So again, welcome here today, part 3 of our stats series, analyze and report data. So we'll just dive right into a different presentation here. Let me close this one and we will kind of continue with these slides that we've worked on the last couple of sessions when we talked about confirming the data that we put in and then also preparing the data for the analysis. So we've kind of already hinted a little bit at the AOV analysis of variance. That's really the big ticket item that we'll do for the analysis. Here kind of want to talk through what that all entails. And if you weren't with us last week, this slide is familiar from last time, but we'll go through it kind of again here to really just explain the analysis of variance that we want to run. You know, with agriculture research, there's of course always going to be variation, and those come from a variety of sources. And so thus the analysis of variance helps us to understand and draw conclusions. So statistical variance is a measure of how spread out the data is about its mean. So the AOV dissects the variability in the recorded assessments. There is controlled variability, and that comes from our treatments and the blocking structure that the researcher had a hand in, that we can control. We decided as part of the trial design. And then the experimental error is the uncontrolled. So basically, we're considering if the observed differences that we have seen are due to chance, then the variance between treatments must agree with the variance within treatments. That's kind of ultimately the big question that we're trying to answer here with the analysis of variance. So I just have an example here that we'll just kind of talk through the calculations, the math, a little bit of what we end up with. So this would be, just an example trial that had 5 treatments, 4 replicates, and we're just, dealing with the yield data at the end of the season. And this would be the type of output that we get from AOV. So just kind of going piece by piece here. The first column, first calculation here is degrees of freedom. And so that is the number of independent comparisons that can be made. It's a little tricky to define, but it's really the number of values in any kind of final calculation that are just free to vary. Really easy calculation for us here with the variance. It's just n minus 1. So for like our 5 treatments that we have, then we have 4 degrees of freedom for the treatments portion. The next calculation is the sum of squares. That represents the amount of variation in the data. And of course, we're splitting that up into each source that is listed in the table. The mean square is the sum of squares divided by degrees of freedom. So we're really taking the amount of variation and dividing it by the degree to which it can occur. Then we calculate an F ratio, which indicates the level of variation from that source compared to the random variation. So the larger this ratio is, the more likely that the variance from this source is not due to just random chance. To quantify this, just how large is large enough, we calculate a p-value, and that is the probability that the observed differences in the treatment or the block, whichever row you're looking at, the treatment means could have arisen by chance. So a low p-value, typically at 5% is kind of the cutoff people use. A low p-value indicates that we can be confident that there are real differences among treatments. Whereas if you have a high p-value, like we have here between the blocks, the 0.61, that indicates that there is no evidence of a real difference, in this case, between the blocks, the replicates we created. This could be that there is no real difference, or that the differences are too small for us to detect statistically based on what we have and what we're running. So to summarize, the AOV analysis breaks apart the variance of the observations into different sources, and then calculates a p-value as the end result. So the big thing is, that p-value is a probability. For the AOV, that p-value is the probability that no differences in treatments exist. So a p-value of 0.04 means we are 96% confident that there are significant differences between the treatments. But we are not done yet. We need to know which observed differences between treatments are significant and which are not. So the AOV analysis itself does not provide an answer about which differences in treatment means are actually significant, just whether there is evidence that there is at least one difference between them. So the next step in the analysis is to run a mean comparison test, also called a multiple comparison test or a mean separation test. These compare the treatment means to determine what differences are really significant. ARM has a variety of mean comparison tests to choose from for different situations and research types. So the most common ones are LSD, Duncan's, Student Newman-Kuhl's, and Tukey's HSD. So obviously, which one do I choose is kind of a common question then. Not a political discussion, but tests can be classified by how liberal or conservative they are, meaning if they are more likely to report a false positive, which would be the type 1 error, or a false negative, which would be your type 2 error. So you should consider the penalty of failure for the study in choosing which test. If the trial is going to be used for registration of a product, then conservative is probably more appropriate. But for a screening trial, it's all about potential. So you're really not too worried about false positives. You're really just looking for that potential, that possibility that it's something is significant there. So you're much more likely to choose a more liberal test. So do have a handout, if you will, if we were all in person, that just kind of goes a little deeper into the mean comparison tests and kind of recaps a little bit of what we saw previously with the calculations and the different components of AOV. So that's a PDF that's just out on our website. We'll also include that link in the recording email that we send out if you want to take a little closer look at that. All right, so let's show an example of how a mean comparison test works. Each test, the specifics might vary a little bit in how it's done or the calculations within there, but the basic concepts are the same here. So first step, a test statistic is calculated to perform the comparison of means. So in our example, we'll use LSD. That's the most straightforward one of the set, which is 5.49 for this data. Then we compare the means using that statistic. If the two means that we're comparing do not differ by at least the LSD amount, then they are not considered significantly different. They're too close together to really separate them. Letters are then assigned such that means with no letter in common are significantly different according to the test. So here in our example to the right, we can say that there is evidence that treatments 2 and 5 differ because there is no letter in common, but there is no evidence of a difference between treatments 4 and 5. They both have the letter A. So that's basically how, at least the end result of those letters, really what is done in the mean comparison test. So we said, depends on the test. There's different test statistics. I think some of them really, instead of one single value like the LSD, it's kind of a sliding, changing value depending on which two treatments you're comparing. So it can get more complicated depending on the particular test. But the end result are the same with those letters letting us know what treatments are deemed as separate and significantly different versus the same, it basically being in kind of the same group. Just a quick warning on the LSD, it's super popular, but I think it's important to kind of draw this one out. The LSD test is really designed only for specific comparisons chosen before the data is collected. So when you're using that to make more than one comparison, like across a whole trial, in this example, the true significance level becomes much larger as the number of treatments increase because there are more and more pairwise comparisons being made. So, the idea of the LSD is let me just compare treatments 1 and 2. I've defined those two as the thing I care about the most. That's great. That's what it's designed for. But really what we've done here in these 5 treatments is we've compared 1 with 2, 1 with 3, 1 against 4, 1 against 5, and then 2 against 3, 2 against 4, etc. It really, really grows pretty quickly how many comparisons are actually being done with that same one value. So although you may say, hey, I'm running a 5% significance level, that ends up not being totally true as you just add more and more comparisons. It's just more and more likely, since it's a really liberal test, it's much more likely you end up with a type 1 error, a false positive with this particular test. So just a word of warning, it's super popular, partially because I think it's so easy. It's a simple measuring stick that you can even look with your eyes to decide, but you gotta be a little careful with it. All right, so that's the theory behind here. Let's dive in then to ARM itself. And here I've got a trial open. It's dummied up, of course, for a variety of things to show people. So I've just got a few different assessment columns, 9 of them, not too many assessments. Calculated yield at the end. I think there's a few other, most of it's, yep, there's some pest severity assessments as well. And then at the end are all kind of the yield columns. So to perform the analysis, we will go under File and Print Reports. And in the available reports, there's a section of Summary Reports. So that is where we will look to find the AOV Means Table. Is definitely the most popular report here that runs the ANOVA analysis. There are a few other summary. There's a repeated measures analysis, correlations, dose response. If you're in a multi-factor design, then you would want that factorial AOV. And the assessment data summary pretty much just gives the data points that were recorded and a treatment mean, but no real statistical analysis. So I've got my AOV means table here. There are a good number of options to choose, and we'll dive into some of these more in a little bit when we talk about the frequently asked questions. But kind of the most top level here is to point out that mean comparison test. Those were the options we kind of called out to. There's even more than just those 4, but these top 4 are kind of the most common, and we did put them in order of how liberal down to how conservative they are. So you kind of get a sense of where you may want to land on that spectrum, again, given your particular study. And then you also have the significance level, or your alpha level, which historically, is usually done at 5%, but depending on, again, that penalty of failure, you might be in a position to change that as well. All right, so I am going to press next. We're going to actually analyze the data. You can kind of see the progress in the little red text down below. What comes up next are the report messages, any feedback for us. In this case, we have some errors. So this is kind of a sneaking in one of the frequently asked questions here that trips people up. And these really are residuals from the older way of reviewing data. We mentioned this a little bit last week in the data review session about previous tools we had in ARM versus kind of the newer ones that have been created that matched kind of the newer statistical routines that are done. And so this is the older way where ARM would scan all of your columns and make recommendations of what actions to take. And if you said no to any of them, then they would just kind of land here as an error. Although I don't think that's quite appropriate per se, a little harsh. I think it'd be more appropriate as a warning because it's not something that we should stop and be particularly worried about. It's just talking about the assumptions of AOV. And actually, in this case, it's testing kind of a different set of criteria than what we would have done in the column diagnostics, which is what we talked about last week. So for a little bit more detail in that and the options of those two different techniques, if you will, check out last week's recording for the data review. So I'm just going to proceed past that. And then on this print dialog, I'm going to preview the report on the screen. So we can kind of see what we get with this report. And let's zoom in a little bit. So if you're new to ARM reporting, we have the top header portion is really the same on all reports. You've got your company name at the top, and then the information entered in the header portion of the particular trial. So things like your experiment title, the trial ID, who is involved, etc. So that's the same on every page. Now for specifically the report itself here for the analysis, we have every assessment column that we had, all of the ratings that we took, show up here as columns in this table. So the top half kind of matches the top half of the editor itself, where we have the header description for the assessment. So what was actually performed, what's the crop, what's the pest, etc. And then we have treatment information. And in the individual columns, then we get our treatment means. So these are the treatment means for each treatment in our first assessment, and then the second assessment, etc. And I'll zoom in a little more to look at the actual values here. And we have letters, which would be the results of our mean comparison test. Then we've got statistics, if you will, the LSD value, standard deviation. You can control what ends up being here or not, depending on what you want in the output. Here I've got kind of the standard ones in addition to the tests for normality and homogeneity variance that we looked at last week. And then the bottom here is kind of a brief version of the AOV table. So we really just see the F statistic that we had talked about before, and then that p-value from the F statistic, both for the replicate and the treatment components. that we kind of had split out. Since this is an RCB design, we've got replications and the treatments that we care about. And that is then just repeated for each column, and I can just pull to the right when we run out of space on the page, and it just starts again for the next assessments. So that's the AOV analysis. We've kind of talked about the components here. Again, all of the, pretty much anything you see in the report has at least one, if not more than one option back on that previous screen that can affect either whether that thing even shows up on the report, or maybe its behavior, the statistics behind it, how it's calculated. So of course that results in a lot of options and a lot of scenarios of different setups. So I've really tried to rig up this trial and my report options to hit up a lot of scenarios that we see very commonly cause questions. And so the number one question by far, it's kind of an overarching question that has a lot of different potential answers to, is where are my letters? That's the number one question far and away, for a variety of reasons. The first one here, I just dialed it up right in column number 1. I'll zoom in one more time. Column number 1, where are my letters? I don't even have a letter in this column at all. What is going on? All I see is this dash where the letter should be. Column 2, I've got letters. Column 1, I don't. So I'm going to close the preview and go back. So we'll go to the previous to see our last step here in the report options. So the first answer with the dash is found under this mean comparison test in our AOV options. There is an option here to specify what ARM should put on the report when there are no significant differences between treatment means. So in actuality, in that column number 1, the comparison test may have been run, but there were no differences that were considered significant. So by default, the default character there is that dash symbol. But you can change it to whatever you'd like. So maybe an NS for no significance, all caps, lowercase. I think you have 3 characters that you can type in here for really whatever you might want to have. So the dash is the default. Another one may just be a lowercase a. If you do that, and I can just preview the report here, it'll be pretty small, but we'll try to zoom in. Using an A is sometimes preferred just because it looks like all of the other columns, and just the fact that they're all in the same group. So no significant, there are no differences, so that all of the A's might be a preferred output. But sometimes it might be nice to really make it pop out on the screen that there is no significance. So I've seen NS uppercase or lowercase. Uppercase really makes it stand out. Is another example of sometimes what people will do, just so it kind of stands out, especially if you had a long treatment list. If you had 20 treatments or 50 varieties in your study or something like that, it'd be maybe a little hard to have to scan through all of the A's just to find out there was nothing that wasn't an A. So that decision is yours, putting that in that little box for what you might want there. There is a question before we move to the next item here. What does use adjusted mean as primary mean do? So this actually ties in a little bit with another option further down with your analysis method. So if you are using the least square estimation, then if you have missing data, what the analysis can do is calculate an adjusted mean. So, and when I say missing data, it either could be that you didn't have a value for one of the plots, or maybe we had to mark it as damaged. Maybe we had to throw it out and exclude it, kind of tying back to our first session on data confirmation. Something wasn't right with a value, so we had to throw it out. Well, in the analysis, it really wants to have balanced data. And so the analysis will make an attempt to guesstimate and adjust the mean to take into account that missing data point. So then you really have an adjusted mean versus the raw or your arithmetic mean of just taking the 3 values instead of 4 or the 4 instead of 5. You have this adjusted mean that statistically is what really should be used in your comparisons. That's kind of the fairest, in a sense, statistically speaking, the thing to use. So this option to use the adjusted mean as your primary mean is recommended to turn on, in that if the analysis needs to adjust based on a missing data point, that really should be the primary mean. That's the mean that we see on the report. So even though this 11.7, if there was missing data, maybe the remainder, the other 3 assessment values I had, their mean maybe isn't quite 11.7, but we had to adjust for that missing value. That's really why you would turn that on. And it is recommended, since statistically that pairs with what we're doing with the ANOVA, is we're going to use that adjusted mean in our decision making. So it's best to use that as the primary mean. If that makes you a little nervous in the fact that you really would like to see a raw mean, there is an option here in the mean descriptions to turn on the arithmetic mean. So that will, that calculation will ignore anything else related to the analysis and just look at the raw data, however many data points you had, what's the average of those, that'll be on the report too. So that can be a nice way that, hey, the primary mean really is whatever the statistical world says we should use, and then the arithmetic mean can be that real life, if you looked at the numbers, this is what you got type of thing. And you can put that beside or under the mean. And just to show a preview of kind of what that looks like, because I think that's a pretty popular one to have that adjusted mean here. So you'll see we kind of segregate that one. All the statistics with that primary mean are on the left, to really draw out the fact that these are the raw means that may or may, really weren't used in the statistics necessarily. And then the primary, everything statistically done, is all kind of grouped together. And you can see I have no missing data, so there's nothing's different in these right here. But if we did have missing data, I think we'd start to see some differences. Great question. Okay, so moving on to the next frequently asked question. Again, we're kind of dealing with the concept of where are my letters? Oh, let me turn off that mean just so we have fewer numbers to look at on this report here. So still looking at column 1, and we've decided, well, there's no significance in this column. Sometimes the question is, well, I'm not getting letters, I'm not getting significance, but shouldn't I be? I'm really looking at my LSD value of that 1.46 and say, well, if I were to manually compare treatment 2, 11.6, to our largest one, 12.5, then, if I'm off a column here, then I should expect to see differences, but I don't. Doing the math, I don't think that's actually true because this would be more of a 13. But in any case, you're kind of using that manual comparison to say, hey, I would expect to see differences based on how spread out my treatment means are, but ARM isn't giving me those letters. It still is telling me no significance. There is a scenario where that definitely can happen, and we would come down to this treatment probability of F, that p-value for the treatments. And in this column, it is 0.6, which, as we talked about in the slides, means it is not significant. So when we ran the AOV analysis and kind of holistically looked at all of the treatments and said, do we think there's evidence? Are we confident that there's any significant differences between these treatments? The answer was no, there's really not confidence in that. We could at best say that we're 40% confident that there could be a difference, which is not very confident at all. So in theory, if the AOV analysis doesn't think there's any differences, then maybe there's no point in doing the next step where we actually run a mean comparison test to find what differences are significant, because we don't think there are any. So that's the logic that is tied to the option here, only when significant, AOV treatment P of F. So this is also known as a protected mean comparison test. To say, we're going to look to see what the AOV analysis said, and if it doesn't think there's any differences, we're not even going to run the mean comparison test at all. So statistically, a recommended thing to do, most especially if you're running the LSD test. So I believe that was the Fisher really had come up with the LSD calculation, and that paired right well with this protected test. So if you're running Fisher's protected LSD test, would be the name you find in your college textbook on statistics probably. That's really how you would accomplish that, is by turning this on. And just the logic there is to not just run ahead with the mean comparison test if AOV doesn't think there is anything. Technically speaking, it is possible to turn this off and run the report, and you may get letters. And in this case, we didn't. I'm surprised. I don't know if I've changed one of these numbers, because I really thought I had that rigged up nicely. But they're too close together even for that LSD. I guess I could tweak one of these numbers, but it is technically possible to turn that off. But just know you're basically begging for a false positive. You're really trying for that type 1 error, because the AOV didn't think there were differences. So you really probably shouldn't keep digging to try to find a difference. So that's why that is turned on by default, at least. But that is a choice you can make in your own analysis. It's just not recommended. All right, moving on to the next question. We're going to actually move off of this column number 1 and go over to column number 5. And then this one is still kind of tied to where's my letters. I've got letters for most of my treatments, but one of them, for some reason, doesn't have a letter next to it. Why am I missing a letter when clearly I have data for treatment 1 here, just like everything else? So how come I don't have a letter next to that? In a scenario like that, I would look towards the ARM action code. Let me zoom out here a little bit. The ARM action codes field. So that's in the header. I'll try to put it at the very top to make it a little easier to see. That's the very, it's actually towards the bottom of the header. And as we go across to column 5, there is a code. As we talked about last week, we used some of these action codes. A lot of them are just commands and instructions to ARM once the data is run and analyzed. So in this case, we have ET1, and that code is telling ARM to exclude treatment number 1 from the analysis. So treatment 1, which is our untreated check, was not included in any of the AOV analysis, the mean comparison test, but we are showing the treatment mean on the report so that we know what happened with that treatment. In this case, this kind of practical example, maybe we're not hoping to differentiate our product from doing nothing, so we left that out. I think this is a kind of getting a sense of what the disease was doing, the percent area, so how much disease we had over the leaves, perhaps. So obviously, that number for the untreated is going to be very extreme, and a lot of times you end up with a lot of interference, if you will. You have a lot of variability maybe in those untreated checks, and it makes it harder to statistically separate the treatments of interest. So sometimes it's perfectly logical thing you might want to drop out the check from the analysis, because really the comparisons we care about are between our different products here. And in this case, it looks like it worked because we actually have some good separation here. And we had a pretty good CV because we've ignored that check. Another option, so we did ET1, that's pretty literal, exclude treatment number 1. You may also see EC. That would be short for exclude the check. So any check treatments, any untreated treatments that are marked in your settings of the trial are dropped out from the analysis. And that would have the exact same effect on column 5 because treatment 1 you can see is our untreated check. So those would be a couple cases for how you might be dropping out a particular treatment. There might be a good reason to do that. And that would result in kind of that blank no letter for that particular column. And we'll just point out on this scenario, and it worked out well for us in this case, because we did see differences. We do have a new statistical tool called planned comparisons. And that's another option for this concept in general of zooming in, if you will, to what you care about most specifically. And just in your trial settings, or if you're planning in the design, so you're more in the protocol settings, you can set up particular treatment comparisons to say, yeah, in this case, I've got 5 different treatments in this study, but our primary interest is comparing Tilt 250 to the, to our tub product that's at the same rate. So really 2 versus 4 is our number 1 priority on comparing things. And so you can use that planned comparisons function to define that. And that's a nice way to statistically zoom in, if you will, to that comparison, but still use all of your data. So you're not throwing out some data points that you wouldn't have to. We probably won't have time to dive into that option, but we'll probably have what's new in ARM towards the end of this year, beginning of next, that we'll spend some good time on that function. One question that kind of clarifies back the last question we had. So the default, I think if you were to load in the available sets, we have like our trial defaults. that does have student Newman-Kuhls as the test, and the only significant AOV treatment PFF are turned on. Those are the ARM, the GDM defaults, if you will. I would say we definitely do recommend using this. The student Newman-Kuhls, I think we chose as a in the middle, maybe a little bit conservative out of the 4 options that we wanted to choose. So we didn't, sometimes that Tukey's is so conservative that you struggle to find differences that really should be there, thus your type 2 error. But we also don't want to just recommend LSD where you're just firing from the hip and super liberal. So yeah, we have the student Newman-Kuhls as the default. But yeah, there's so much kind of nuance to statistics. It's some of these, it is like, yeah, you probably should have it on. This is probably the best way to do it. And then some of them really are a gradient, if you will, of different choices to choose from. And it's just kind of the pitfalls, I think, of statistics in some ways. Hard to give a straight answer sometimes. But I think this is a very nice, safe thing to turn on. And if you don't have any other guidance from industry or your protocol designer, student Newman-Kuhls is a nice, fairly safe, but not too safe option, I think, for your test. Would be our not super official, but our recommendations overall is a nice approach there. Great question there. All right. Another frequently asked question, and it's actually, I guess, less of a question, maybe just kind of finalizing these ideas of where are my letters? What do I do? Oh, we do have a question here before I move to that next one about regression analysis. And I believe that's kind of on our big picture as an item in the toolbox. That'd be nice to add. I don't believe that we're like on the cusp or, adding regression as we speak. But I think we're looking at that with some other statistical tools as well for putting that in there. In general, we do try to have reasonable tools in ARM. We don't want it to be like exactly like SAS or something where there's 18,000 different ways you can run statistics. We try to balance between being powerful and having options for people, but not be overwhelming and too many options. So it's a tough one to kind of do that. So all right, so the last item in this thought process of kind of analyzing why don't I have letters? How can I get letters, etc., would be that there is a post-hoc analysis that we can do. And that is found here in the descriptive statistics. I'm going to turn a bunch of these off just so we can kind of focus in. There were so many values before, but I am going to turn on this post-hoc power analysis. Excuse me. And on the report then, there's actually kind of a couple things that'll pop up in the analysis. So if we look at that column number 1, where we struggle to get our letters, we have a couple new rows. There's a minimum replicate and a largest mean difference. And then there's also something here in the LSD as well. So the largest mean difference, this is going to point out, looking at all of our treatment means, what is the largest difference? So if we were going to separate any treatments, which two would it be, and how big of a difference is there between the two of them? And in this case, it's 0.93. So the mental math there of doing the treatment 2 versus treatment 5, we ended up with 0.93 was the difference. And then we have a percent, that's a 7% of the grand mean, which was 12.03. If we compare that to the LSD, which we could be using to compare our treatments, we see the LSD was 1.46, which is 13% of the grand mean. So considering our LSD is the measuring stick, you need to be at least 1.46 apart from each other for us to see and understand that to be a significant difference. Since our largest was only 0.93, we never found significant difference. So that post-hoc is kind of after the fact, looking at the statistical power we had. Oh, this makes sense why we never found any differences. Why we don't have any letters is the differences were just too small for us to detect any significant differences. And so then we have a minimum replicates. So it kind of rolls a whole power calculation. If you have more replications, given the same parameters of your alpha level and your statistical power, and the number of treatments that you have in this study, if you created more and more replicates, you would gain more statistical power because you have more data points to split apart that variance and understand what's happening. So in this case, if you did that power calculation, you would have needed 17 replicates to get that LSD value, that stick of measuring stick, down small enough to detect a 0.93 amount of difference. So kind of in other words, yeah, we never saw a significance. We would have needed a lot more data points to really have any hope, if you will, of getting significance just based on the amount of variability that we experienced. That CV kind of ties into it, and things like that. So this post-hoc can be kind of a nice tool to, not a whole lot you can do now, for this particular trial. Maybe there are several other trials at different locations that were run, and those can count. So if we pool together different trial sites and do a multi-trial analysis, we might get significant difference, and we can draw some conclusions that way. But at least in this single trial, there's really no hope for this particular assessment. Whereas some of these others that we did see significance, we only needed 2 replicates. We only needed 3 replicates. So you kind of can use the calculations as a plan for a next year idea as well, to say, well, just based on how things shook out, we really needed more replicates or maybe more trial sites. So this post-hoc is done in a particular trial on the report. If you want to follow that up with kind of a more holistic calculation, there is also in your trial settings or protocol settings on the design tab, there's a power and efficiency. And it's that same idea we just talked about, but kind of before the fact. So you can put in your parameters of what CV you would think you'd have, how many replicates do I want, and put in your statistical parameters, and it'll tell you how many reps you need, things like that. So we won't go too far into that, but just to point out that there's other tools kind of help you start thinking about next year and plan for more if you didn't get the statistical outcome you needed. All right, one more frequently asked question. It's not quite the where are my letters, and we've touched on it just a little bit with the arithmetic mean idea. I might turn that back on for us, but there are some scenarios, and in addition to that primary mean, where we might not recognize that number. That can be kind of the question. I don't get what number is on the report. That treatment mean is not what I'm expecting when I just look at the data I collected. Those aren't matching up. Why is that number not the mean of the data I took? So we talked through the missing data and that adjusted mean that we can do. One other situation, and let me zoom in a little bit because we have that here in column number 4. So the primary mean's 2.31, whereas the raw, the arithmetic mean, is 2.5. And you can see all the way down, there are slight differences, some larger than others, between the mean here that's used statistically and the arithmetic mean that we would expect if we were just looking at the raw data. So this example ties into the action code again. And this time we are running an automatic log transformation. So this may very well have came up from our last session with data review. Maybe the homogeneity variance assumption was not met. So we needed to apply a log transform to be able to trust our analysis. So what we end up with on the report, and is signified by this DAL, it's a D-transformed mean. And I think we have a footnote here. Let's see if it shows up on, yes, it does show up with the preview. This D symbol means that our treatment means are being reported in a D-transformed data unit. So coming back to that column, what that means is we take our raw data points and we are applying a transformation to every raw data point before we do the analysis. In this case, it's the log transform. So I think it's log of x plus 0.5, I think is what it does. So then each value is transformed through the log transformation. Then we can calculate treatment means from the transformed values and then run all of that through the AOV analysis. And we get mean separation letters, which are right here. And we could put on the report those log transformed means, but that would make very little sense to a human reading the report because I can't think of the terms, is this the percent? I can't think of a percent of a log value or a log of a percent value. That doesn't make any sense to me in real life. So we de-transform and kind of do the inverse transformation on those means to get something that actually makes sense. This is a 2%, a 21%, et cetera. It can actually make sense to us. But mathematically, since we ran it through a transformation and then back the other direction, you don't end up right back where you started. It's a weighted mean. So that's why you may see values that in some regards don't make sense. They're not the raw values. And so that's in part why we added this arithmetic mean option. So again, you can see just raw values. What was the mean of the observed values? That's available in the arithmetic mean. And then statistically, it's more valid to show these mean comparison letters with the numbers that actually were used in those comparisons, or close to it, since really in this case, they're de-transformed. And that's also why we see this weird LSD value, because there's actually a range. So this first row here is our LSD. And when you're doing a de-transform, then you can't just use one LSD value, because it depends on the actual log. When we were dealing with the log numbers, there was one LSD value. But then again, just the way the math shakes out, you end up with this whole range, depending on if you're comparing small numbers versus large numbers. So in some regards, it kind of makes a mess, if you will. And so then we're really just translating back into something that makes sense to compare. So on the left, you have kind of that whole statistical world, and then you have on the right that just arithmetic, the raw values that might make more sense to a person that's reviewing the data, or reviewing the analysis, I just say. And then there are little T's next to some of these other values, that like your standard deviation, CV, and grand mean. And just to point out, same idea here. And if I go down to our footnotes, we can see that T is pointing out that mean descriptions are reported in the transform data units. So they're not being de-transformed. So you can't, they won't quite match up. They're a lot. In this case, since it's the log transform, they're much smaller than what you would expect just looking at these numbers. And that's the reason why is there's this transformation there. Question here, kind of really last week, that if you're transforming the data to satisfy assumptions, going through the different columns, should you aim to check the same transformation for each column? So I guess really looking at maybe your assessment type, it probably does make sense if you've performed the same assessment several different times. I think it would make sense to consider using the same transformation then on each one of those if you're kind of going to compare each of those side by side in the sense. I think it would make a lot of sense then to do the same action to each of them since they are similar, and maybe you would kind of compare them to each other as time went on in the season or something. So I think that makes sense to me. I will say, caveat, I'm not a statistician. so that's more of an intuition answer than a statistically rigorous one. If you have access to a statistician, they might be able to help you recommend that. But I think it makes sense to kind of do the same thing if it's the same type of assessment. But I don't think the entire trial, if you run into one instance where I need a log transform, I don't think you need a log transform every column just blindly, but instead it would make sense only to do it when it needs it based on the column diagnostics. And yes, to answer the D transform, it is back transform. So doing the inverse of whatever transformation you did. In this case, it would be taking the exponent. There's a square root, so then you would be doing the square backwards. So yeah, it ends up just being the math of it all. All right, well, we've reached our time, so not too surprising. I got a little long-winded. If you did have more questions, I guess I apologize for running a little long. Feel free to send us an email if you did have more questions, but I really appreciate the ones throughout the session today and over the last few weeks. So hopefully we'll be seeing you all again at our next round of October webinars coming soon. So thanks, everybody.